first part, that is k nearest neighbor. Okay. So, so this is a, representation of your data basically. So let's say you have, some data which has some x values and, y values, right? So let's say, um, you're trying to classify, so you're doing a biological experiment and you are checking that, what is the, so you have some set of mices, right? So you have some mice, and among those mice you are trying to see, like, you are given data about the two genes of that, of all the mice. Okay. So let's say gene 1 and gene 2 data you have, right? So, and you're trying to classify them, that whether, if any of the gene is making them, obese or not. Let's say obesity of mouses, right? Mice. So, basically class B, the green class, let's say these are the classes of, mice which are obese, and the red class, is the classes of mice which are not obese, right? So on the x-axis you plot gene 1, on the y-axis you plot gene 2, right? So class A, as I said, is not obese. So what does each of the data point means, right? So this is the, let's say x-axis is the value of gene 1. So gene 1 value is this, okay? For this point, for this mice, let's say this is one mice. So for this mice, gene 1 value is this, and gene 2 value is this, whatever is in the y-axis. And similarly for all the other mice, okay? Now, you see the green class, as I said, is the classes of mice which are, obese. So, so you can, like, get an idea by visual inspection that, the classes which have higher percentage of gene 1 and, lower percentage of gene 2, these are making the, mice obese, right? On the other hand, the mice which have lower percentage of gene 1, whereas higher percentage of gene 2, they are not making them obese, right? So this could be one of the, practical examples that we see. Okay. Now, is that clear? Okay. So, feel free to stop me whenever, you have a question or something. Okay. So this is your data, right? So you have plotted your data in X and Y axis, and you are just getting, visual inspection for it. Now what happens is that you are given a data for another new mice. Okay, let's say, some other mice which was not present earlier in your data, right? So now you're given the data that, okay, this mice has this percentage of gene 1, this percentage of gene 2, right? And you have to predict whether that mice would be obese or not. That is your problem statement, right? So what you do is that you know what is the percentage of gene 1 in that mice and percentage of gene 2 in that mice. So you again plot the value of gene 1 and gene 2, and you plot the, position in that xy plane, and this is what your position is. This is the new example that you get. Okay. Now you have to classify this example, and you have to classify whether this mouse will be, obese or not, whether this mouse will fall in class A or class B, right? So this is your problem statement. Now what you do is you calculate, uh, the distance of each of these, uh, mice from this new mouse. Okay. So let's say, distance of this, new, mouse from this green one is something, let's say, 1. And, I'll come to what I mean by distance actually. Okay. I'll come to that. So, but let's say this distance is 1, this distance is, let's say, 1.5, this is even further. So this distance will be, 2, and this distance is even further, let's say 3, and so on, right? So distance is basically, what you physically see, right? Distance from one point to another point, right? So how do you calculate the distance from, one point to another point, right? So in Euclidean plane, uh, if we have some, if you have 2 points whose coordinates are, let's say, x1 y1, and another point has coordinate x2 y2. So the Euclidean distance between them is x1 square, x1 minus x2 whole square plus y1 minus y2 whole square, right? That is the Euclidean distance. That is basically the what you call the distance between the 2 points, right? If you take a measuring tape and you measure the distance between the 2 points, that is what you get, right? That is the Euclidean distance, right? So this is the distance measure. This is actually the formula. So in 2D plane, that's what the formula you use: x1 minus x2 whole square plus y1 minus y2 whole square. But in in a n-dimensional plane. So this data is very simplified because we have only two dimensions to this data. But if you have like gene one, gene two, gene three, and so on, 100 genes, let's say. So you have to get an idea of how to get the distance for that 100-dimensional data, right? You cannot plot a 100-dimensional graph. So there should be some way to you know uh, measure the distance between 2 points in a n-dimensional manifold, right? So this is the measure of distance. So this is summation of ai minus bi whole square by some normalization constant ri square. So this is the range of the ith component. So this is how you basically you know if without this Ri, this is just the Euclidean distance, right? This is just summation of ai minus bi whole square. That's what you get in case of a Euclidean distance, right? But this Ri, what is the significance of this Ri? Is this Ri is basically normalizing uh, all the parameters, right? Is that fine? Okay. So why do we require this normalization? One thing is that all these genes, gene 1, gene 2 might have different ranges, right? So let's say gene 1 has range of between 1 to 10, whereas gene 2 has range between 10 to 100, right? So since these have different ranges, we want to normalize the data so that all the uh, values are normalized to some within some fixed range, let's say 0 to 1. Okay, so that is why we do normalization. Otherwise, distances could be very over measured sometimes, because when you're taking gene 2, since the since the range is too high, that will increase the distance abnormally, right? Whereas in case of gene 1, it will not. So basically a little separation between two genes would be magnified basically in case of gene 2, whereas it will be undermined in case of gene 1. uh, can we normalize using other statistics like standard deviation instead of range? Yeah, of course. Yeah, we can. So yeah, there could be many ways of normalization, but the idea of normalization is basically that you want to have your data, all the features under the same range. Okay, that is the idea, so that you're not getting magnified or undermined in some of the features. So basically you're giving equal weights to all the features, right? So that is the idea. So yeah. So after you calculate the distance to from this new example to all the other examples, you see what are the nearest neighbors of this new example, right? So if the data points are, so someone is asking, Dhanya is asking, if the data points are widely separated, how do we normalize? Yeah, so no issues. So if some data points are widely separated, so so basically, let's say, you have some wider separation in one of the axes. Let's say in the x-axis, your data is like separated from here to here. So there is a wide separation, right? But in the y-axis, you have relatively, you know, smaller separation, smaller width. Okay. So basically, what you do is that you can uh, you can use the this width. Okay. So what is the separation in the x-axis, and you divide that uh, using that width. So that is basically this width is basically your Ri. That is the range. Okay. So what is the range in the y-axis? X-axis is this range, this whole range, this place where you get the first uh, red point until the end point. So this is the range basically. You can see my if you can see my pointer, okay. So there is one line. I don't know if I can draw a line, but let me try. Okay. So yeah, if you see this is the range in the x-axis, right? So you can see the line, right? So this is basically the value of Ri. R1 basically. So in the x direction, only this x direction range is this, whereas this is the range in the y direction for the gene 2, right? So because this is the range across which this uh, values are present. Right? Okay. So I hope this is clear. Okay. Okay. All right. Now, yeah, after you have, normalized your data, calculate the distance. Now, now you have to choose how many nearest neighbors you need to consider, right? You want to consider basically. So let's say you consider three neighbors, okay? So you want to say that, okay, I will consider only the nearest 3 points to my new data point, right? And I want to see what are they classified as. So if you see the smaller circle, this is the k equals to 3 circle. So these are the three nearest neighbors to this new example. So if you see among these three neighbors, two are in class B, one is in class A, right? So what you see that, okay, my nearest neighbors are in class B. So I should also be in class B, right? So if I have, you know, I'm closer to class B than class A. So that is what you get. So you classify this example as to be in class B, right? So that is the idea, right? This is the algorithm. This is it, right? So if you have any questions, ask me now, or we'll go deeper into it. But this is what is being done in the algorithm. This is all. Okay. Okay. Now, if let's say you want to take more neighbors, right? Instead of three, you feel that okay, three is not enough. I want to have more neighbors in to consider my classification. So what you do is you go to higher neighbors and you try to see. Let's say you take k equals to 7, right? Now you consider the seven nearest neighbors. So this is the circle within which all the seven neighbors lie. So 1, 2, 3, 4, 5, 6, 7. Okay. And out of the seven neighbors, you see that four are in class A, three are in class B. So now uh, your prediction changes. Now you see, okay, now I have four neighbors in class A, whereas three neighbors in class B. So this I must be in class A, not in B, right? So what was this? Why the difference is coming? Why, if you take class k equals to 3, you are being predicted in class B, but if you take more neighbors, you're getting predicted in class A. So why is this difference coming? And what is the optimal way to choose the value of k? So you don't know like which value of k you should choose prior to, in prior, right? So in prior, you just have a data, you get a new example, but you don't know which uh, k value would give you the best result, right? So that is basically the question, how to choose the k. So I'll come to that later on. So I'll do a hands-on, Python tutorial after this. So I will explain it like how to choose the value of k and what is the best k that you should have, right? But in the meantime, you're free to come up with your answers or your what do you think. So please let me know in the chat or so okay, this is a Voronoi diagram, I think. So basically, these are the examples. So these points, if you see black dots, so these are the examples, the data points in the xy plane. And these cells, if you see the colored cells, these are the cells which define like in which is your nearest neighbor. So basically, if you are falling in this green cell, so basically your nearest neighbor would be this green dot, right? So this dot. Whereas if you are falling in this violet cell, your nearest point would be this dot. So this is just a representation to see that uh, if you have your data set like this, where if you have a new example coming in, which is the nearest neighbor to this example and which are all the nearest possible neighbors. So this is just a representation. This is just to visualize things, but I'll come to the hands-on part where you will see like how we do it. So in the meantime, Mainak is asking, is K a hyperparameter? Yes, it is a hyperparameter, and how do we determine the values of hyperparameter? I think it was covered in class in the previous weeks. So it is by cross validation, right? So we'll see like how we do that, right? More number of neighbor A is in case equals 7, but yeah, right, V is right. That's why we classify it as class A in one case and in class B in another case. But one thing to note is that, in k equals to 3, if we are looking at, lesser number of neighbors, you know, intuitively, don't you feel that we are like, overfitting our model, right? So, because if let's say instead of k equals to 3, even if you lower the value of k, if you take k equals to 1, then what happens, right? So, you are saying that okay, my nearest neighbor is in class A, so I'll be in class A. But you ignore all the, let's say, 10 other nearest neighbors. So if you ignore only the nearest neighbor, very nearest neighbor, first nearest neighbor, you are classified as in class A. But if you, let's say, consider, other neighbors as well, which are not as near as the first neighbor, but, pretty much near as well. So if you consider those neighbors as well, you might be classified as class B, right? In a different class. So you have to see that, if you're lower value of k, you are kind of, overfitting your data, right? So a very low value of k is also not a good idea. Right? So we'll see why is it overfitting, and so when I say overfitting, then the terminology that should come to your mind is variance. So if you have attended the previous weeks, you should know what is bias and variance, right? So the term that should come to your mind when I say overfitting is variance, right? And when I say underfitting, it's bias, right? So lower k values gives you a high variance, and a very high k values gives you uh, high bias, right? Because it is underfitting your model. You're taking into all the variables, all the data points, and you're also fitting the noise and everything. So you're kind of getting an average estimate. You're not classifying it very accurately. Right? So, okay. Now, I will talk a little bit more about the distance measure in KNN algorithm, and then I will just go on to the hands-on. So, right now, what we saw is that this Euclidean distance measure, right? So, this is the distance measure in all the axes, and you square them and finally take the square root. This is basically the Euclidean distance. As I said, if you have 2 points, you just take a measuring tape, measure the distance between the 2 points. That's what you get. Uh, so there are two other, concepts of distance in which you can measure your distance. One is the Manhattan distance, which is basically just the modulus of the difference between the 2 points and summation over all the axes. So this thing is, we have to square and take square root, square and sum, and then take square root. In this case, you don't square it. You just, take the modulus of the distance between the 2 points. This is the Minkowski distance. This is also known as something as LP norm. So if you are familiar in linear algebra, it's called LP norm. But yeah, if you haven't don't have any linear algebra background, don't worry about it. It's just a name. So what you do is that it is similar to Euclidean distance, just in the place of this square, this two, you just take any other integer. Let's say p, right? So it could be like p could be 3, 4, 5, 6, anything, right? And then you just take the 1 by p times. So this is just another measure of uh, distance. There is nothing special about it. Depends on your problem to problem, like which measure of distance would give you the best estimate. But apart from that, I think yeah, I think This can also be treated as hyperparameters. You see, like this P parameter, this could be treated as hyperparameters. You can like fit your Canon model on different, with different P's, and you will get with some P's you can get a better result, whereas for some P's you can get a not so good result. Okay. So, okay. Now these are the concepts of distance. Now, what about, let's say, you have some features which are more important than others, right? So let's say you have so in the previous example, if you say, gene one and two, right? So if let's say your gene one has more importance in determining whether this mouse is obese or not, right? So what you will do is that you will obviously give more weightage to gene one and less weightage to gene two, right? So you don't have to like earlier. What we are doing is that we are giving equal weightage to all the um, all the features, but you can give higher weightage to some feature, whereas lower weightage to other features which are not as crucial as crucial as the others in determining the uh, obesity of the mouse or anything, right? So how do you weight your you know um distances basically, right? So that was one way that which I was saying, that giving more weights to features. Now we'll see that instead of giving more weights to features, we can also give more weights to data points. Okay, so if you, let's say, you want, in this example, so you want to give more weights to the nearer points. Let's say you have fixed some value of k. So let's say you're using kn with k equals to 7, right? So basically these are all your points. Okay, and but you can choose to have all the points uh, in your while determining your new example, right? So you can choose all the points, but you can assign different weights to different points. So for example, for the nearer points you can assign higher weights, whereas for the further points you can assign lower weights, right? So in that way also you can do kn. In that case you don't have to fix a particular value of k. You just have to fix your weight so that it gives more weights to the nearer points and lower weights to the further points. So this is, if you see this table, distance weighted kn. So this is how you decide your weight. So weight is inversely proportional to distance squared. So distance. So if you see, like, if you have nearer distance, smaller distance, your weight will be higher. Okay, because the denominator is more. Sorry, denominator is less. Your weight is more, right? And then you calculate the this weighted distance to all the points. You sum it up and you see whether that will be in class 1 or class 2, or class A or B, whatever, right? So that is one way to do it. Another way could be, find this, fix this weighting functions. So these are fixed quotient, fixed y square, adaptive quotient, adaptive y square. So I'll just briefly explain like what it does, from a physical point of view. So you see, if you consider, look at this graph at the bottom. So this is your new example. This cross, this X marks the new example that you have to classify, whereas the dots are the examples which are present from earlier, right? So this is what your weighting function would look like if you are fixing it with the quotient function, right? So with the quotient function, if you see, this is exponential of minus, this is dij, this is the distance between 2 points I and j, divided by b whole square. So b is kind of the bandwidth. So I will tell what this physically means, what this bandwidth physically means. So dij is clear, right? It's the distance between the 2 points. So we just saw like how to calculate the distance, right? Now we'll use the distance to calculate the weighting function, right? So b is some basically fixed value. Okay, this is a constant. You can choose it on your own. So, but this is how this wij will look like. So if you see, so from the cross, as you go further, your weighting function is decreasing. So that's what I was trying to say. So you're giving more weights to the nearer points, whereas you're giving lower weights to the further points, right? And this is how it is decreasing. So this is how this exponential of minus this part looks like. This whole function looks like, right? Now, if you increase your b, So what is the physical significance of B? Is that if you increase your B, this distribution will become, broader. This is basically the bandwidth, right? So this distribution will become broader. Whereas if you decrease B, this distribution will become sharper, right? So this is how it is, right? And then adaptive Gaussian is just, this will depend on the value of k that you choose in your KNN algorithm, right? So this is the same, but just, for if you choose a particular k, then you can, like, it will depend on that. The bandwidth will depend on that particular parameter. Okay. So here the b is constant, whereas here the b can change, right, for different points and so. Well, okay, similarly for pi square, what happens is that if you look at this function, this is 1 minus distance by, again, bandwidth whole square, uh, total square, if dij is less than b. So here what happens, if you choose a bandwidth and, if your distance, if your points are within that bandwidth, it will have some weight. Whereas if that point is beyond that bandwidth, it will assign a weight of 0, right? So this is basically cutoff, right? Beyond which your weight is 0. Whereas if you are within this bandwidth, your weight is calculated like this. This will also have, give more weights to the nearer points and lower weights to the further points, right? Okay. So is that clear, or should I, like, draw some graphs and so on? Like, I can do that as well. But is it clear from what I said? Distance measure not clear? So which part? Is it the Euclidean distance or the weighted distance, or all the three? Okay. Let me just quickly, open this. Okay. Let me just tell you how to, calculate this. So, so let's say again, you're classifying your mouse. This is the gene 1 value. This is the gene 2 value. Right? So let's say you have like 3 points, 3 mouse. So, let me, so these are the red points are in class A, the black point is in class B. So 1 point is in class B, whereas 2 points are in class A. So now let me tell you the coordinates of the points. So basically this has coordinate, let's say gene 1 value is 5, gene 2 value is 4. This one has gene 1 value as 4, gene 2 value as 6, and whereas this point has gene 1 value as 2 and gene 2 value is, let's say 3. Okay. So this is how it looks. Okay. Now you have a new point. Okay. So this is your new point, right? So this has some coordinate value of, let's say, uh, you know, something between, let's say, 3 comma 5. Okay. Now, what is the distance between this point and this point? So this is just the Euclidean distance, right? So the Euclidean distance will be just, x1 minus x2 whole square plus y1 minus y2 whole square. Yeah. So this is basically 3 minus 2 whole square plus 5 minus 3 whole square root. So I'm not normalizing it here, but you have to, normalize it as well, But so first, basically, what is the idea is the first you normalize all your data and then you take the distance. So this will come out to be root over of 1 square plus 2 square, that is root 5. Right? So this is how the Euclidean distance looks like. Is that clear now? Okay. Okay. Now, similarly, you can calculate the distances to this point and this point, right? Okay. So quickly, if we see the distance between this point is root over of 4 minus 2 whole square plus uh, 6 minus 3 whole square. Yeah. So that is root over of 2 square plus 3 square. That is equal to root 13, right? And this one, this distance is root over of, uh, sorry, am I? Okay, so sorry. So this is the coordinate of 3 comma 5, right? Okay. So this is 4 minus 3 whole square, 6 minus 5 whole square. So yeah, this is the coordinate, this and this with what we're comparing. So 4 minus 3 whole square plus 6 minus 5 whole square, right? So this will be again 1 square plus 1 square, that is root 2, sorry. Right? Okay, I think this, right now, okay. Now this distance, this is 5 minus 3 whole square plus 5 minus 4 whole square, right? So this is again root over of 2 square plus 1 square equals to root 5, okay? So this distance and this distance are equal, both are root 5, whereas this distance is root 2, so it is even smaller. So this is the closest point, right? This is the closest to this cross, okay? So when you're using weights, right? So what will happen is that you are giving higher weight to this point, whereas you are giving lower weights to the remaining 2 points, right? So when you are calculating the weighted distance, basically you just put the value of dij in the weighting function that I just showed you, and you get some weight for, let's say this is point 1, point 2, point 3, and the new point is, let's say, you know, x, let's say call it x, okay? So now the weighted distance would be basically, mhm, yeah, it's okay, like 4 minus 5 whole square and 5 minus 4 whole square is same, right? You're saying this is 4 minus 5 whole square, right? Is that what you're saying? Yeah, 5 minus 4 whole square is same as 4 minus 5 whole square. So since this is a square, you don't have to worry about, you're taking 5 minus 4 or 4 minus 5. It's the same thing, right? Okay. So yeah, this is basically minus 1 whole square, right? So minus 1 whole square is 1, 1 whole square is also 1, so you don't need to worry about it. Now, yeah, with the weighted, so what you will do is that, calculate the weights, and you will do W of x1 into D of x1 plus W of x2 D of x2 plus W of x3 into D of x3. So basically W of x1 is the weight that you assign to this line. So that you can calculate from the formula, the weighting Gaussian, or whatever you take it, by square, whichever weighting function you take, that you can calculate from there by putting in dx1. And dx1 we already calculated, that is root 2. Okay, this is root 2, and again this is root 5, and this is again root 5, right? So this is how you get the weighted distance, right?